Good morning, one and all present over here. First of all, I must thank the organizers of IWCSET for giving me this opportunity to talk in front of you. Thank you very much. Today, I am going to deliver my guest lecture on a topic entitled Chitisan and its modifications for water treatment. This is Professor R.M. Zugade from Department of Chemistry, Rashtrasant Tukroji Maharaj, Nagpur University, Nagpur. Let us start with what is chitosan. Chitosan is actually the second largest available biopolymer in nature. It is obtained from the crustacean shell wastes. Chitosan can be modified into this obtained from the crustacean shell in two ways. One method is the chemical method and second one is the biological method. In the chemical method, the crustacean shell waste is treated with HCl and then NaOH to carry out the demineralization and deproteination of the material. This gets converted into chitin. The chitin is the basic polymer which is further treated with either NaOH or with chitin deacetylase, which is a protein or what we call as an enzyme to convert it into chitosan. So this is how chitosan is generally obtained from the nature. If we compare the properties of chitin and chitosan, chitin is actually the acetylated type of biopolymer, whereas if we deacetylate it, it gets converted into chitosan. It has got NH2 group and OH group as functional groups. If we compare the properties of chitin and chitosan, if we see this, chitin is hardly dissolved in water, acids or alkali, so its solubility is negligible, whereas if you see the chitosan, it is poorly soluble in water but it dissolves in acid to some extent. If we consider the molecular weight of chitin, it is of the order of about 1000 kilodalton, whereas for chitosan it is of the order of a few hundred kilodalton. The absorptivity of chitin is negligible in most of the solvents, whereas the absorptivity of chitosan is 1 to 2% in many of the solvents. Important properties of chitosan which makes it an important material for adsorption of materials, adsorption of ions as well as molecules are the hydrophobicity, biocompatibility, biodegradability and non-toxicity. It's highly reactive because of two important functional groups present in chitosan, the one which is NH2 group and second is the OH group. Because of these two groups, it is very important material for adsorption process. Its chemical structure allows specific modifications to design polymer for selected applications. The reactive groups are able to develop composites with different compounds. Like many of the metal oxides, they form composites with chitosan. An important property of chitosan is after adsorption of the metals or any of the molecules, it can be regenerated and reused. So all these properties make chitosan an extremely important adsorbent. Native chitosan can be used as an adsorbent. We will be discussing about various forms of chitosan as an adsorbent for various environmentally important metals and non-metals. So if we see this native chitosan as an adsorbent, the presence of NH2 group and OH group makes it an extremely important ligand because of the lone pairs of electrons present on NH2 group as well as OH group. Various models have been suggested for the entrapping of these metal ions into the matrix of chitosan. Two important models I have cited over here from literature. One is called as the bridge model, where if we see an important metal which is environmentally important is copper, cadmium or lead, such metals get trapped into the matrix of chitosan by the bonding with NH2 group and OH group. This model is called as the bridge model, and second model is the pendant model. In bridge model, there are two chitosan chains, and in between this copper ion has been trapped by the coordinate type of bonding, whereas in case of pendant model there are two water of hydration associated with copper and only two bonds are formed with OH and NH2 group. Both the models are available, and this leads to good adsorption capacity of chitosan towards cadmium, then lead, nickel, etc. These are a few references from the literature from where I have taken this. But in order to enhance the adsorption capacity of chitosan, various modifications have been suggested. The first modification, which is the simplest type of modification in chitosan, is cross-linking. So using multivalent ions or multifunctional organic compounds as cross-linkers, we can cross-link the chitosan chains to enhance the stability. So increasing the structural stability and porosity of the material takes place because of cross-linking phenomena. For example, sulfate, phosphate, iron, which is multivalent cation, these are multivalent anions. They, as well as the organic compounds like formaldehyde, epichlorohydrin, etc., they can be used as cross linkers. So two various number of chitosan chains get cross linked with either the multivalent ions or the organic molecules, and this leads to a crossed type of structure. We have carried out certain experiments with chitosan. This is our own work. So we have converted chitosan into a sulfate cross-linked chitosan, and we have used it for the removal of chromium 6 ion, which is actually present in the form of chromate ion. So, and we got a very good adsorption capacity of our chromate when the sulfate cross-linked chitosan is obtained, whereas the native chitosan has got very poor adsorption capacity of 2.48 mg per gram of chromate ion, whereas sulfate cross-linked chitosan has got a very good adsorption capacity of about 156 milligram per gram of chromate. Another important application of sulfate cross-linked chitosan is the use in the Congo red removal. Congo red is an important dye which is generally present in various waste waters, and in order to remove it from the waste water, we have used the same sulfate cross-linked chitosan, and we have seen that this sulfate cross-linked chitosan has got a very good dye adsorption capacity of the order of 91 milligram per gram. This is our own work again. Another example or another way of cross-linking is using the multivalent metal ion. So what we have done is we have used stannic ion SN4 positive as a cross-linking agent for the removal of arsenic 3, which is very important, environmentally important metal ion. And if we see the adsorption capacities of this stannic cross-linked chitosan, this forms, the stannic is used in the form of stannic chloride SnCl4, and the material which is formed is used as an ion exchanger with the arsenite ions. The adsorption capacity, if you see, for a native chitosan, it is just 1.83 milligrams per gram of arsenic, whereas if we see the cross-linked chitosan, it is enhanced to about 17.1 milligram per gram. This is the important application of cross-linked chitosan. Another cross-linked material we have used the chitin as a chitin material or chitin based material cross-linked with stannic ions and converted it into stannic cross-linked chitosan, SN4 cross-linked chitosan, for defluoridation application. And we have seen that the SN impregnated chitosan, which is cross-linked chitosan, gives a very good defluoridation capacity of 14.77 milligrams per gram as compared to the native chitosan, which is about 2.84 milligram per gram. Another way of modifying chitosan is the impregnation phenomena. If we impregnate the molecule with certain reactive groups or reactive moieties or charged moieties, will increase the electrostatic interaction with the ionic pollutants. For example, if we see this hydrous ZrO2 impregnated chitosan beads for the removal of fluoride ions. So it's a combination or impregnation of ZrO2 on chitosan material, and it leads to trapping of fluoride ions. This is a reference taken from literature. Second way of or another example of impregnation of chitosan with quaternary ammonium compound, it is ethyl hexadecyl ammonium bromide. This is our own work for removal of cadmium and mercuric ions from wastewater. And again you will see that chitosan flex, which is a native chitosan, gives a very low adsorption capacity for cadmium and almost no capacity for mercuric ions. But when this is impregnated with EHDA IC, then it gets converted or the adsorption capacity increased to very high value. This is our own work. Another example I have taken from literature is mixed metal oxide impregnated chitosan beads for arsenic removal. Again, it's a combination of metal oxide impregnated on the chitosan material, and again it has got very good adsorption capacity towards arsenic, an environmentally important metal ion. These are the two modifications, the cross-linking and impregnation. Whereas the third modification is the synergistic effect of cross-linking and impregnation. Cross-linking leads to structural stability, whereas the impregnation leads to increased active sites. So it is possible to introduce ionic groups that will specific towards the desired species. This is our own work. What we have done is we have impregnated ionic liquid, which is aliquot 336, on sulfate cross-linked chitosan. So we have cross-linked chitosan. Along with that, we have impregnated it with this particular ionic liquid, which is a quaternary ammonium type of ionic liquid. And we have seen that the chitosan flex have got very low adsorption capacity towards chromium 6, whereas when we go to the impregnated as well as cross-linked material, that is a synergistic type of material, it gives a very high adsorption capacity of about 250 milligram per gram of chromium ion. Another example of this type of impregnation as well as cross-linking, what we have done is we have cross-linked the chitosan with phosphate, and then it was impregnated with this particular material, which is the ionic solid, and ISPC cross-linked chitosan. So what we are getting is a very high adsorption tendency towards chromium. The fourth way of modifying chitosan is the formation of chitosan composite. The composite formation leads to the chitosan chains are actually composited with various types of materials like graphene oxide, bentonite, etc. And it gives a very good adsorption tendency for various materials. These are very large number of examples are available in the literature for chitosan based materials for the removal of various toxic elements as well as molecules. Other applications of chitosan, which are mainly the biomedical applications, involve or use tissue engineering, wound healing, cancer diagnosis, vaccine, etc., and large number of applications are also available for this particular molecule. Thank you very much for your kind attention, and for any query regarding this particular topic, feel free to email me at ravinj2001@yahoo.co.in. Thank you very much.